There we go. And you should, every once in a while, because this course is a bit dynamic right now, because we're finding our way through it for the first time, or I am. So I'll put an updated syllabus. If anything changes, check this date here. And this should link you to the syllabus, so that you can see what the most recent version is. And here, so we had image quality, which you all did remotely, and then the first lecture on nuclear medicine on the principles. I'm assuming that for some of you, there may be some questions about the image quality lecture. We could do those today. I don't think I got any in the mail. I emailed out an announcement. Did everybody get the announcement that I emailed out? Okay, great. So if there's something that you want to go over again from that, that's fine. We can go back to those slides and do that. And then the beginning of nuclear medicine, we did totally remotely. So we'll continue nuclear medicine today. For some of you who took 280A, there'll be a bit of a review in the sense that we're going to look at the projection slice theorem again, because it's probably the singularly most important concept in both CT, PET, and nuclear medicine. Is how does the projection slice theorem work, and why can we produce images from projections, essentially? Has everyone been able to get access to this book on RedShelf? Any problems doing that? No? Great. So we have two books that we're using. This one you have access via RedShelf. If we need something from the Bushberg textbook, which is a textbook about this thick, I'll put a PDF on the site and point you to it. The Bushberg textbook, as I said last time, is more from a medical physics background, in that it's very descriptive as to what's going on for a medical physicist. The Prince and Links, Jerry Prince is an electrical engineer, and this book is great because they get down to algebra / formulas and actually try and give you an expression for what the signal would be in an image, and then how do you modify that expression. So if we zoom in here to the where we're going to keep going with nuclear medicine today. I hope to get homework 1 out by this evening. I want to go home and work on it. And it'll mostly be problems about looking at image quality and how to measure it with simple image analysis software. And then next week, we'll do nuclear medicine applications. And as we saw in the introductory lecture, a huge amount of nuclear medicine is done in cardiology. And then the other major application for nuclear medicine is cancer and trying to find tumors. We'll then look at some comparative testing and image quality, basically about segmentation. Segmentation is the process of taking an image and selecting different tissue types and just isolating those tissue types and making a model based on that. And it's a huge part of medical imaging in research, is getting the segmentation done properly. It has been basically an unsolved problem for about 50 years. There's no algorithm that just works 100% that you would agree with when the result comes out. Usually you have to go in manually and tune it up, right? Tune up the segmentation, which is a pain in the butt. And it makes the expense of doing quantitative imaging very high. It's when you get humans involved in segmentation. For a project, if somebody wanted to do a project about teaching a deep learning network to segment something simple, we could talk about getting you a set of pictures where you could use those as examples and try and get a network to segment it. And it seems to be the, by far the most successful method of doing it thus far. Then we're going to go back to nuclear medicine briefly, look at PET and PET CT, and then have a quiz on that. So that's what's ahead of us for the next couple of weeks. If we go to the Canvas site, let me close that. Those of you who have noodled around and looked at it. So here are the PDFs of the actual lecture slides that have been used. You have a YouTube link to the movies, and you can zip, I would recommend that you watch the movies in 1.75 or even 2x, because it's kind of like I drank 50 coffees that day, and you just zip right through it. It's still perfectly understandable, but it's not at the slow, normal talking rate. Very interesting fact. Watch it at 2x for like 15 minutes and then go to 1x. It's hard to listen to. I mean, they sound kind of, drunk, basically. Just like, everything's going so slowly. So watch it in 2x. And then if there's supporting documents, like for lecture 4, I'll try and label which lecture they're supporting. So today, there's a PDF out of the Bushberg textbook talking about this generator that generates the contrast agent for nuclear medicine. And I'll add stuff as needed to that. Any other questions about the setup? No? Okay, great. So we have 4 people live online. Can somebody in the chat tell me if everything's going well? You can hear me and see everything okay? Okay, terrific. Thanks so much. So now let's go to PowerPoint. So we don't have any questions about image quality or the first nuclear medicine lecture. Nothing stacked up there. No, this all looks good. Great. All right. So again, here's what nuclear medicine looks like when you're imaging somebody's chest. We have injected an agent into the person such that they are glowing. And most of the time, say for body SPECT or single photon emission computed tomography, the energy of the photon that will come out of the patient is at 140 keV. And it's a gamma ray. It is at the top end of X-ray energy that you create with an X-ray tube, actually 140 keV. But an X-ray is created through mechanisms using the electrons in an atom. This 140 keV photon comes out of the nucleus. And so you can call it a gamma ray, even though they have the same energy, because it's through a nuclear transition that this comes out. However, once it's a photon and it's 140 keV, it's going to behave like it doesn't remember where it came from, right? It's just a photon. Off it goes. So it's a pretty high-ish energy X-ray gamma and low-ish energy gamma ray. And so it can exit the patient. However, some of it will be absorbed, right, by the patient. Right? And so you'll get a shadow of the patient from the inside out, right, when you're making this picture. As we saw in the first lecture, it's very important to have this set of sepia so that when you detect one of these 140 keV photons hitting one of your detectors, you know it came from a position that is essentially orthogonal to your detector. Okay, what we want to build up is a collection of samples of photons that come from a straight line directly perpendicular to the detector. Okay? If it's coming at an angle, we don't know where the heck it came from. Right? You just don't know. So here, this sepia is very important. We get an event, and we know it came from somewhere along this line. We don't know that it came from here, but we know it's somewhere along here. Right? And then over time, as we saw in the first lecture, you will build up a total signal along this line, which is just integrating the brightness at every point along that line mathematically. Okay, so I've got, you know, a whole set of brightnesses here, and then they're going to show up as the sum here after we've collected at this angle. For traditional SPECT systems that have sodium iodide crystals here, it takes about 20 minutes to collect all the data, because you have to build up your detection of the counts. And so you'll set this at a certain angle for, you know, a minute or something, or some short time, then click, do the next one, click, do the next one, and you get through to build up a set of projections. Okay. So where does this stuff come from? This is from the Bushberg textbook. I just captured some figures. We'll see which chapter it is later. But so how do you have this radioactive fluid that you're going to inject into the patient's bloodstream? Where do you get it? Excuse me. Short answer is for SPECT, or for single photon emission tomography, it gets delivered once a week, right? And it gets delivered in this container, right? And actually there is a small nuclear decay going on inside this container for that whole week. And the tech is going to go up to this and pull out a certain amount of material to image, and it will have a decay rate itself, the stuff that you pull out. The stuff that's in here that's decaying into your contrast agent normally has a much longer half-life than the contrast agent you stick in the patient. You want the contrast agent to go in the patient to have a short half-life, short-ish, so that they're not exposed to radiation over a long time. So you just want the radiation while you're imaging, and then you would like it to be gone as soon as possible. So this arrives once a week at your lab. Inside there, inside that container, you know, this is a radiation-proof container because you want to contain all of, if someone is carrying across the room, you don't want radiation coming out of it. You basically have the molybdenum is this little pellet here is a material that's made actually in a nuclear reactor, and you extract it from that and put it here in this pellet, and the molybdenum is going to decay into technetium, which is the material that you're going to inject into the patient. So this transition from molybdenum to technetium occurs all week, and as the technetium is building up in this thing here, it basically, when you flush it with saline, you can chemically keep the molybdenum on this filter, and the technetium will come out. Okay, and so what you get out here, you eluate or whatever, is the technetium that you're going to inject into a patient, and this is the elutant that you're going to wash through this in order to bring it out. So this, I forget what the half-life, we might see it on the next slide. Okay, so this is molybdenum 99. Again, molybdenum 99 and technetium, the material that we're going to inject into the patient, well, it's actually this one here. They have 99 nucleons in the nucleus of the atom. Okay, we haven't changed the number of nucleons in this transition, but what has changed is the fact that in molybdenum, we only had 42 protons, and now we have 43 protons. Okay, so a neutron changed to a proton through beta decay, which means there's a whole set of possible beta decays that occur when you actually measure this. So it ejects electrons, right, with different energies, right? And all of these are going on simultaneously, but there is a dominant process, and it's this one. So, you know, close to 90%, I think, of the electrons that are coming out are these ones that have this energy transition, right? And it leaves you with a new nucleus, right? It still has the 99 nucleons. However, we now have 43 protons, and it leaves it in a state that is unstable in the sense that it's in a higher energy state than its rest condition or its baseline energy. And so the nucleons themselves, the protons and the neutrons, are interacting with each other through strong forces. That's what's keeping them together. And when that beta came out of the nucleus, it left that nucleus in a higher energy state than its base state. Okay, and there are many possible higher energy states that it can be in. And then, so we're here, and it's called technetium-99M, which means it's in this higher state. Okay, and a lot of it is in that higher state. I think it's about 80% of it is in that, or 88 or something. So over time, with a half-life, a specific decay period, this technetium-99M will decay to technetium its baseline state. And that stuff is really stable. That's like 10,000 years or something. It just won't decay. You won't get radiation out of it anymore. This is called an isometric decay in the sense that you don't change the number of nucleons, or you don't change the substance itself. It just, a photon comes out, a gamma ray comes out, yeah.
Actually, what is the precise difference between technetium-99M and technetium-99? They both have the same number of protons at 43 and the same mass as 99.
That's correct.
What are their exact differences?
Well, the interesting thing is the truth of the matter is, if you read about this, nobody will tell you what the exact difference is, because you probably have to go into quantum mechanics and nuclear physics to figure out what is the state of those nucleons together, and why is that energy level a condition that nucleus can be in.
So technically, put it simply, in TC and technetium-99M, it is an excited state.
Correct.
While the technetium-99 itself is on the ground state.
That's correct. And all of these states of technetium, right, are excited states. Okay, so each one of these is technetium in an excited state. And this energy difference is the mass difference between, you know, the excited state and when it goes to the ground state. And that energy comes out as a photon when that happens. So it emits a gamma ray at this energy bloop, when it drops into its ground state. There's many, many different transitions that can occur in the nucleus to, you know, have this happen. However, this is the dominant one, right? This first beta decay with molybdenum, and then you have this technetium. It's got a 6-hour half-life, I guess what that is, and going to its ground state. And so here's a simplification of that. In that, okay, so 88% of it goes to this technetium-99M, all right, which is this excited state. It decays into the ground state with a half-life of 6 hours. So half of it's gone in 6 hours, 75% in 12, et cetera. And then once it's in the ground state, molybdenum can go straight to the ground state, and 12% of it does, right? And this ground state has a half-life of, you know, 20,000 years, right? So it's not going anywhere. Right? I think the most stable nucleus is iron. I think that's the one where if you just let nucleons evolve thermally forever, everything would turn into iron, right? Because that's where they would all go, where That's the tightest configuration with the minimum energy. Every other nucleon is kind of in an excited state compared to iron. Although, don't quote me on that. That's just from a podcast. So I don't know. Okay, so any questions about that? This is one example, right? Technetium is a substance that is, I don't know, maybe 75% of nuclear medicine or more is done with technetium because it has the properties that a 6-hour half-life means it's easy to work with. You don't have to run down the hall with your agent because it has a 12-minute half-life and inject it into the patient and image them right away. The 6-hour half-life is kind of leisurely. You can leave it on the shelf for an hour, inject it into the patient. I mean, it's decaying away, but there's still a lot of radiation there. And in fact, you can do a stress test where you can inject it and have the person get on a bike and do stress, right? And it basically stays constant over that work period. And you can use it to measure whether or not the material is taken up during stress. Okay, so now we're going to look at the data itself and how do you make, in the nuclear medicine lecture, we talked about, do I have a picture back here now? Sec. This, okay, this came up in the lecture itself, where here's our object or our patient where we have no agent in this part, got some kind of baseline amount here and then a hot spot here. And we get the number of counts are plotted as a function of position along this projection, okay? This is exactly what happens with computed tomography after you take the logarithmic transformation of the ratio of the photons that get absorbed versus the photons that went in. You make this same plot, essentially. So we're going to do a little review on how a function like this is used to make a two-dimensional picture from these 1D projections, right? In some ways, I guess it's common sense that you should be able to do this. For very trivial examples, you can see how it works. Like if it's a dot, you can see where the dot is after 2 projections. But it's not patently obvious that for a continuous profile like this, if you took different profiles at different angles, you could make an arbitrarily high resolution picture, right? All right, glasses are fogging up here. Okay. So we have, oftentimes this coordinate along here can be called R along the projection direction. Sometimes it's called L actually in CT. But for each value of theta, we're going to select a set of thetas. Let's say we'll select, 500 thetas, and we'll click the detector into those 500 different positions and collect data, depending on how high resolution you want. In nuclear medicine, you probably don't use 500. So here is the actual data that is acquired, right, from these different projections. So each rotational angle of this, of the view of this data is what was detected by the nuclear medicine scanner. Let's just pause it at one spot, say here. So for the detector, remember, is a 2D array. So it has, Y in this direction, X in this direction, right? No, don't use that, sorry. Let's call it something else. This is Z. Let's call this slice in this direction. And then this along here is that R direction along the detector, okay? Let's go back and look at that detector here, the R direction here, okay? And we're going to get a stack of these, right? Which are the different slices of the patient, okay? So here, this is Z or the slice direction, this is the R direction. And then as I go across here, I see it gets brighter here, gets darker, gets very bright right here, darker, bright, etc. So that's the profile, okay, in terms of how that's organized spatially. And then what we're doing here is showing, after I move my detector to a different view angle, what that profile changes to. Okay. So here, my detector would be looking straight at the patient. But the patient, say the patient's lying on this table with their head here. The detector comes down, I'm looking straight through their left arm, right, off this way. Their chest is here and their back is here. Looking at that, so that when I rotate up to look completely from the anterior view right down through the patient's chest, we can do that by rotating our detector to that coordinate. I'll say that. Right now we're looking from the top of the patient down. We're going to do that over 180 degrees. Look at all the views of the patient. Okay. Is that clear what the coordinates are there? So all of the reconstruction we're going to do in 3D for when we're talking about this is assuming that we're extracting out the projections for a specific slice, and we'll do our two-dimensional reconstruction of that slice independent of what's going on up here and down here. We're just going to look at that slice. Okay, so it's going to be 2D reconstruction. In general, if you have a point source like in CT and you have this, you basically, it's a cone of radiation coming out. But here, because we have these sepia on our detector, we can look at this and say, well, all of the stuff coming at any point in this 2D plane came straight up through the patient. Okay, so they're parallel beams through the patient. We don't really have a cone of radiation coming. Okay, and you can kind of just gestalt the spatial resolution of this technique just by looking at these projections, right? You're not going to miraculously find super high resolution features from raw data that looks like this, right? If those high resolution features aren't in your raw data, they're not going to miraculously appear when you do back projections or different angles. This view that we're looking at right now is classic nuclear medicine called the Anger camera. Before they did reconstructions of 3D, data sets, they would just do one view and just look, at that single view. Specifically, if all you're looking for is one hotspot, if you want to decide whether or not, say, a primary tumor has thrown a met to the liver, right? So you have a metastasis of something that's gone from your brain tumor down to your liver. You do one of these and you just look for a bright spot in the liver, right? And it's a binary decision. So you don't really need high resolution. You just need a yes or a no. Right? And so one view actually serves that function. Right? If what you want to do is look at the relative brightness of different parts of the heart, then you pretty well have to do a three-dimensional reconstruction, because this is a confusing signal. I mean, it's the buildup of activation through a very large chunk of heart, right? So you want to isolate it more. Okay, so this is, for each one of those angles, we get one of these views, okay? This is extracted straight out of our 280A course. You'll remember it, those of you who took the course, in setting up the geometry of doing computed tomography. And I put it here because a lot of what we're going to talk about next is precisely the same as used in computed tomography, in that once we modify our data that we measure in computed tomography, we get a function that is essentially equivalent to brightness in nuclear medicine, or sort of intensity of radiation at a point, right? In CT, it was amount of attenuation of X-rays at a point. And when the X-ray attenuation was high, that the value of that function was high. It's kind of in the opposite direction, but the value of that function was high. And when the X-ray attenuation was low, the value of that function is low, and that's this function here. So just to review, here's our coordinates x, y now. X can be right, left, y can be anterior, posterior. Okay, so I have basically an axial cut through here. Let's forget about what's going on towards the head and the feet. We'll just look at the single plane. And in X-ray imaging, you send an X-ray into the patient, and you know what the intensity of the X-ray beam you sent in was, and that's this value here, I0. And then on the pathway through the patient along this line, what emerges are fewer X-rays. I've never seen imaging where you generate X-rays by shining X-rays into a patient, right? MR, that actually happens. You irradiate the patient with radio frequency, you turn that off, and then the patient radiates back radio frequency, which is pretty cool. Here, what happens is you have fewer X-rays at the exit point, and you can measure a function based on that. So the number that emerged from the patient right here is this number. It's however many you put in times the integral of the attenuation as you go through here. And that's dependent on what kind of tissue it is. If there's bone in here, if there's a rib right here, you're going to have high attenuation, right? So you take the ratio of the amount you put in, or I'm sorry, the amount you put in as the normalization factor for the amount that you measure coming out. So here it is here, ID over I0. You take the log of that, and it gets rid of this exponential decay term, and you get a function that's proportional to essentially the constant in the exponential decay, which is the relative ability of that tissue to absorb X-rays. And so we get a function where it's high, where you get a lot of absorption, and low, where you get a little absorption. And then these are the coordinates that we usually use. So we have L along this direction and theta, which is your projection direction. In nuclear medicine, exactly the same thing happens in that here's our object, fxy. We're going to take different angles and get these different projections. And the brightness now, or the height of the projection, is proportional to the integral of the brightness as we look through a view. So right here in the middle of our projection, which is, say, this detector here, we go through and we say that's proportional to the integral of all the brightness coming from here. Right? Obviously, the resolution changes a bit as you go deeper into the object, because a volume that's emitting radiation here can kind of slip in to the sepia, whereas when it's closer to the sepia, it's it basically is more localized, right? So these are fed into a back projection algorithm to give you this image, these different views. When you have a single point, it's easy to understand why back projection works. In that, if I know a priori I have a very small object, I really only need 2 views, and it'll tell me where that object is in the plane, right? If I have a complex object, obviously I need more views. As I get more views, and I just project those views back, I will get a hot spot where my object is. And if I do many angles, I'll get a representation of the object, which is a blurry version of this dot. Okay? And this is from the lecture on Tuesday. If we look at this object and we stack these functions, right? I'm just going to stack them as a function of changing theta, right? And look at that 2-dimensional function. I get this thing, and this is called a sinogram. So theta is changing as I go in this direction, and this direction is position along the detector. And so as I move, I'll see at certain angles, for example, say this angle along here, when the detector's set here, this object and this object will be completely overlapped. I'll be right there, right? When my detector has the L direction along here, or in this case, R, sorry, L and R are gonna flip around a bit. So I have my detector along here, this projects down, that's when they're the farthest apart here. If I take the simplest way to reconstruct the image, and it's called back projection. We'll look at it in a bit of mathematical detail. When I do that back projection, this is the picture I get of this object. So not great. It's okay, right? But it's not great. So we're doing something wrong in just back projecting these views to make a picture. So this was the slide in which we introduced these filter kernels to make SPECT images. And we're going to understand by the next 20 minutes or so, we'll understand why these kernels are introduced, okay? And there's a ramp filter. It's sometimes called a Ramlock filter from its CT generation. And then there are these filters in which higher frequencies are attenuated in creating the picture. But the interesting part about all these filters is as we move to lower spatial frequencies, we eventually get to 0 at the origin, right? So the DC component is wiped out from this. Okay? You can see with the ramp filter, we get a picture that while you don't lose any information, the picture quality itself is not great because there's a lot of noise, right? And so humans, when they see something like this, they reject it. They don't like it, right? They can't create a filter in their brain to get rid of that noise. It just stands out front. Sometimes you can do pretty well just by standing back and squinting, right? You'll filter something. And so the reason there is all the high frequencies. If you stand back, your optical resolution or your eyes just won't work as well at that distance, and things get blended together. And when you squint it makes it further. So that's one way you can do it. And you'll see some radiologists, they'll move their head back and forth at a thing. There was, when, I don't know if it's still done, but some people, when they're looking at specific high resolution pictures like mammograms and stuff, they'd have binoculars and they would sit, to get the perfect viewing distance. Instead of wearing glasses and going straight up to it, they'd sit back comfortably and have these binoculars and read it like that. So I don't see people doing that much anymore. But we're going to understand now why you use these kernels. And okay, you guys still see this. Move that down there. Good. All right. So this is we're going to understand the projection slice theorem, which is a really useful piece of information, a useful theorem. And the first thing we're going to do is look at, in the coordinates that we're used to, the two-dimensional Fourier transform of our image. Okay, so here's the image of the patient that we desire, the true image, and you can see this is just stolen from the CT lecture, right? In that for nuclear medicine, this is activity or number of counts. So mu in nuclear medicine is just how many counts do I get at XY, right? So this could be like, I got 1,000 counts, from, or photons captured from this point. So it's brightness as a function of position in the plane. That function has a two-dimensional Fourier transform, and we'll plot it over here in spatial frequencies. And this, remember the coordinates here, this is in, say, centimeters, right? X and Y can be in centimeters or millimeters. KY and KX are the spatial frequencies. And that's often given as line pairs per millimeter, right? Or radians per millimeter. It's a wave, you know, how many cycles do I get per millimeter of that wave? It looks like a lot of algebra on here, but it's pretty well first year calculus. So what we're going to do is also look at the Fourier transform of this object in polar coordinates in the Fourier domain. Eventually, we're going to look at that, such that any point in the Fourier domain, kx and ky, right? That position, kx and ky, can be encoded with what is essentially a radius in the Fourier domain and an angle, right? So it's polar coordinates in the Fourier domain. And so I have this function, and it's entirely equivalent to this function, right? If you look at it, you know, sitting on the plane, I can basically map it out in polar coordinates, or I can map it out in Cartesian coordinates. The thing that's fascinating is that if I take projections through my image, right? And so these are the integration of the brightness as I move down this line, right? And take all that brightness and integrate it up, and I measure it in my detector here. I get a one-dimensional function, right, of these projections along my detector L at this projection angle theta. If I take the Fourier transform of this one-dimensional function, right, I get another one-dimensional function, and it turns out that that one-dimensional function is a sampling of the Fourier transform of the image at that angle, right, in Fourier space. That to me is not intuitive. I don't know if that's intuitive to anyone here and you can explain it with intuition. I'd love to hear it. It's not that intuitive to me, but you know, I guess it makes some sense in that all of the information, you know, integrated down here is lost into a specific, you know, sort of integration of buildup here. So anyway, this is called the projection slice theorem. And that means when you write it down, this is what it says in just algebra, in that when you take the 1D Fourier transform, which is this operation here, right? We're integrating, you know, over DL over this direction with the standard Fourier transform. It gives us this sample here through the middle. Let me think. Yeah, okay, so let's pause and take a look at the two-dimensional Fourier transform, okay? So again, here's X and Y, these are in centimeters, okay? If I have an image, a two-dimensional image that looks like this, right? So it's essentially a plane wave with a specific frequency. When I take its Fourier transform, if there's a non-zero DC component to this thing, I get a peak in the middle, and then I get a point on either side, which is this frequency, okay? And so these are kx and ky in cycles per millimeter. I don't have any value of points off, you know, the ky equals 0 point here, because there are no vibrations when I go up and down this way. It's all a plane wave. And so in the two-dimensional Fourier space, I get these 3 points, right? When I angle a wave at 45 degrees, what happens when I take the two-dimensional Fourier transform of this is that I get a peak here, which is, you know, the distance from the origin here are the cycles per millimeter along that wave, right? And then if I add these two together, a plus b, and I get this function, then because the Fourier transform is a linear operation, you just add these two results here to get the final 2D Fourier transform. And so I have a brighter DC point, and then these would be, you know, if these two amplitudes are the same, these would all have the same amplitude, all 4 points. So you can see, and I can build up any function I want here just by using different plane waves. And that fills in every point in the 2D Fourier transform. So let's go back. Now that we've looked at the 2D Fourier transform, here's our two-dimensional function. We take its 2D Fourier transform, and I get some function over here. Right? Remarkably, when I integrate the brightnesses along here and make a profile, take the 1D Fourier transform of that, I get a sample through that 2D Fourier transform. So this tells you, in a way, well, yeah, we should be able to reconstruct our original 2D image. I should be able to reconstruct this from the projections, because when I take the Fourier transform of the projections, I'm actually sampling through the Fourier transform of the 2D object. So if I take more of these projections, I'm going to sample more parts of the 2D Fourier transform, right? I'll sample them along these radii. Let's see. So in some way, it makes it intuitive that, hey, if I take a whole set of these, you know, in a propeller fashion around the Fourier transform, I should be able to take the inverse Fourier transform of those data and get my two-dimensional object. Right? Okay. So let's go back. We're gonna, before we look at that, we're gonna go back and look at back projection and see what is wrong with it, right? So here, remember, back projection works just great if you have a dot, but you get a blurred version of that dot, right? It isn't the reconstruction of the true dot. It's actually a version of that dot that has a lot of signal outside. That makes sense, right? Because in back projection, if I take the signal and I spread it over the entire column, right? I have non-zero data outside here, and there is no data out there. Right? So that's just wrong, right? It's an estimate, but it's wrong because I get data in the background. So while this is building up, to my point, I do see that there's all of this data out here that has positive signal that should not be there, right? So that's not the correct way to do it. This is from Prince and Links, and algebraically doing what we saw in this diagram. Okay, what you do is you take your projections, right? The G, remember this is G, L, and theta. And what we're going to do for a specific location along the detector is we're going to map that brightness into all of the X and Y points, right? That go through the field of view at that angle. All right, so I have my projection along here, and what it means to do this back projection, this is a more complex object, so I have many more of these signals, is that I create a two-dimensional picture, this B, theta, X, and Y, from this one-dimensional GL theta by mapping the same value along the orthogonal to the detector direction. Okay, and that mapping is done quite simply by this, right? So now I have X and Y values. I've taken a 1D function and made it 2D by mapping it out, replicating the values in the direction perpendicular to the detector. So when you do a back projection algorithm, for every value of, for every value of theta, we're just going to add those up. I'm just going to put one down, and that next one on top of it with the next value of theta, next one on top of it with the next value of theta. And that gives us this object, which is the laminogram, it's called, which is the sum of these back projections. And we get this, right? And it, again, you're quite familiar with this now. in that you have brightness where brightness should be, but you also have a lot of brightness outside, right? And so the edges of these circles are blurred, and there's a lot of stuff in the background that should just not be there, right? And you can see why, because there's a lot of stuff put into the background around your object or around your target. So how do we do this in a better way? Okay, or in the correct way, basically. So let's review our coordinate system. I've got a projection direction here and an angle, right here. I take its one-dimensional Fourier transform, and it gives me a sample through the two-dimensional Fourier transform of my image. So one way to reconstruct this would be take these data that are on these radial lines. Those are the data we measured, right? If I take the 1D Fourier transform of every projection and I organize them in this fashion, right? Then I have this radially sampled Fourier transform of the object, right? And in some ways, that's a more accurate representation than the sinogram. The sinogram is the stack of data as a function of theta, but it doesn't really have any physical relationship to what's there, right? It's just a way to stick your data in the computer, is the sinogram. Here, if I put all of these projections radially in one plot, and then I put them all, I took their Fourier transforms, and now I got a Fourier transform of the object sampled along these radii. But how do you view that on your computer? Right? If you want to see a picture of that raw data, what do? Yeah, have to put it on a grid, right? Because computers are on grids, right? There's pixels along X and there's pixels along Y. And when you plot it up to make a picture of the intensity as a function of position in the plane, you got to put it in that Cartesian coordinate system to stick it on your computer, right? So in going from here, we need, say I want this point in my rectilinear grid for the Fourier transform, then I need to look at this point, where it is in space, in Fourier space, and then interpolate the values around it onto that point, right? So I do some kind of interpolation of these values, right, onto this rectilinear grid. And an interesting thing occurs, right, in that if I'm close to the origin, so I want to interpolate a point right here, I have a very high density of measurements. I got a lot of measurements, right, because I've got all these data points along here. However, out at the periphery, I may not even have a point, right, very close. It's out here, and so I'm a fairly good distance from any actual measured point. So it's this variable density that is the key to how to do this reconstruction correctly, okay? One correct way to do this reconstruction is to use a very good interpolator to take these data and put it onto a Cartesian grid, right? And then take the two-dimensional discrete Fourier transform, inverse Fourier transform of that grid, and that makes your picture, right? That turns out, because of the small errors in this data, that turns out to be not to be a stable way to do it, right? Because these, mathematically, you look at it and you say, oh, okay, I've got this radial sampling here, but oftentimes it's slightly not, these points might not go through the middle. You have some very tiny errors in the Fourier data. And so when you do this interpolation under the assumption that your machine is giving you this, you get some artifacts in the pictures. So what is done instead is the back projection algorithm is done, but it's modified to correct for the fact that we have a lot of density of data in the middle. Okay? And so what we can see here is, if this is our brightness, as this is our image, so our image, well, how do I go back? Our image here, okay, mu xy. Okay, that's it, right? We know it is the inverse Fourier transform of whatever its Fourier transform is. Okay, so this is just a statement of truth. There's no real data or anything here. This is just the relationship that exists between the Fourier transform of your brightness you're trying to make, right? This is the Fourier transform and the brightness itself. It just follows this equation, right, analytically. If we look at this relationship in polar coordinates, right, which is our data is in the polar coordinates, right? So we're going to make this transformation. Kx is k cos theta, ky is k sine theta. So now we have k and theta, and we map that Fourier transform into that coordinate system. This is what we get. So we integrate from theta 0 to pi, and from k from minus infinity to infinity. Okay, and we change the argument in the exponential of the inverse Fourier transform by this relationship to go into polar coordinates. So this is our original k vector. This is what it is in polar coordinates. And then when we look at the Jacobian for this integral, right? So you need to, once you do a Fourier or a coordinate transformation, if you're going to integrate in your new coordinates, like polar coordinates or spherical coordinates, whatever, you have to change the Jacobian, right? So what happens here is we get this is our new elements of integration where the Jacobian is k. Okay, when you take the derivatives here, you find that this is k. So that's what the inverse Fourier transform looks like in polar coordinates. Okay, and then there's a couple of relationships here, sorry, where we know, sorry, from symmetry that the projection along L at some value theta is equal to the projection at theta plus pi, just with L flipped. The direction is flipped. So when I go over 180 degrees, all I do is flip L. Okay. And so that in the Fourier domain tells us this. So given that, we now have an appropriate way to use the samples that we can easily derive, which are the Fourier transforms of our projections, which is this function here, right? So here, we'll just write it down again. Here's our inverse Fourier transform of the Fourier transform of the projections, gives us the image, right? Swap out our, we'll put in L for the x cos theta plus y sine theta. So I have an L here now. And I can group, I can put k in front of here, right, and dk here, and I can look at this integral on its own, right? So I can take this integral first, right, across this sample, and it gives me this function here we're going to call g prime or g asterisk L theta. Recall it's not GL theta. We know GL theta is the inverse Fourier transform of this thing, right? Of this big G, right? This guy with the asterisk is the inverse Fourier transform of K times the Fourier transform of GL theta, right? So it's this K that changes everything. Okay, so now instead of taking the inverse Fourier transform of just the Fourier transform of the projection, we multiply by k first, take the inverse Fourier transform of that, right? And that's going to give us this function, which is different than our original projection, right? The other way of looking at it through, because the convolution, through the convolution theorem, you can perform this operation just by using the original projection and convolving it with the inverse Fourier transform of K. Okay, if you want to do it in the spatial domain. Because the inverse Fourier transform of the product of two functions, right, is equivalent to the inverse Fourier transform of both those functions convolved with each other in the spatial domain. Yes.
Is the star mark in the G star equation, is that a convolution or multiplication?
It's actually just a label. So this is just saying that G, little g.
It's under that, like the G L theta star.
Oh, this?
Inverse Fourier transform.
Oh, got it.
Convolution.
That is a convolution. Yeah. Thanks.
Does not mean like it's the right convolution another way.
Yeah. So I don't know, I grew up writing it with a star, but so now we have this inverse Fourier transform of the function K, or y equals x, right? Magnitude. So it's something that goes up like this. It's at the origin, and it goes up like this. It's this ramp function. And that gives us essentially a kernel in the spatial domain that you can convolve your projection with and then do your back projections. Okay? So what it looks like is, so here in the, basically in the Fourier domain, we have these radial samples. They have much higher density at the origin, and so you're multiplying them by this ramp function before you take this inverse Fourier transform. So let's look at a couple examples here. Let me see what time we're at. Go to 10:50. So if our original projection looks like this, so this is our brightness. You know, we have a lot more brightness in the middle. Did you have a question? Sorry. No. Okay. When we take its Fourier transform, we know this is a projection or a sample through the 2D Fourier transform of our object. Take the Fourier transform. So here it is. We multiply it by K, which is, you know, or the magnitude of K. So that's just a simple multiplication. So for those of you who like to think of this as filters, this is basically a filter, right? And it's a filter that crushes everything in DC. Like we basically have no zero component here, and then it amplifies the high spatial frequency. Not a commonly used filter, right? Because basically it's going to make everything noisy, right? And it gets rid of all the mean value of the object. So we multiply by that filter, take the inverse Fourier transform, and we get this set of modified or filtered projections, and we back project those, right, to get the object. The other way of looking at it in the spatial domain is if I look at what is the inverse Fourier transform of this thing, right, and bring it into the spatial domain, I can then convolve my original projection with this function, the inverse Fourier transform of this thing, which is the ramp. Looks something like this. Take that convolution, right, and I get, it's the same way, or I get the same functions on the back end, right? It's these G star L thetas, and I back project those. So you can do it either in the Fourier domain or in the spatial domain. So here's some examples. Again, we use these in CT as well. So here's a projection through the object. This is obviously a simple object. It's, you know, some kind of circular object in the middle of the field of view. And when we back projected these, remember we got a bright middle part, but then we got stuff in the background, right? Because it was projecting it all the way through the background. When I take the inverse Fourier transform of the ramp and convolve it with this function, it looks like this. That's a completely different function. Right? That is not, so obviously back projecting these was a bad idea, right? These are the things, given the algebra, that we want to back project. And happily, it has a flat top, which, you know, basically our circular object, where we're imaging, probably has a flat top. And it has these very deep negative lobes that will take away signal that's on the outside after this back projection, right? And then as I add more of these, you know, at better and better angles, I get a higher resolution estimate of my object. Here's a more complicated object. We looked at this before with that set of projections, right? And this is its sinogram. So this is R in this direction, theta in this direction. So that's what the raw sinograms look like. When we do this convolution with the inverse Fourier transform of the ramp, this is the function that results. This is the new sinogram. So you can see it has basically DC of 0, right? And so that when I back project these, right, I get a much better representation of the object. And so this is what the new G star L thetas, when I look at them in the whole plane, the things that I'm going to add up, they look like this. They have 0 in the background. And if I have 40 of them, 80 of them, 120 of them, right, we get a closer and closer representation of the object until finally you get the whole object. Okay. So that is, it's called the Ram-Lock filter in convolution back projection. Okay. And that is the fundamental filter that will give you the actual object. It's the highest degree of accuracy to reconstruct that object for the brightnesses as a function of position. The unfortunate part is if you use this filter, while it's accurate, it emits a lot of noise, right? So if your original data is kind of noisy, this will blow that noise up so that the picture will look very noisy, right? And so normally what is used is, instead of this hard cutoff at the highest frequency here, you'll roll that cutoff off so that those high frequencies are suppressed somewhat. It is key to make sure it still goes back to 0 here, right? That was the fundamental difference between, you know, doing the raw back projection of GL theta versus G star L theta, was this, you know, taking the DC out. And then if you want to make it even smoother, you can do something like this, right? Where we still have the key part of this where DC goes down to 0 here, but then at the higher frequencies, we're going to suppress those frequencies such that the image comes out more averaged and smoothed over space. Okay? And so again, this is classically the way to look at this is it's a filter, right, kernel, right? And so this is done a lot in nuclear medicine, is that these high frequencies, as we saw in that slide very early on, are suppressed, and it makes a picture that's easier to look at. Right? And you can see that the convolution kernel here has, in the Ram-Lock, has a lot of wiggles on the outside, right? Amplifies a lot of stuff. Here we get a kind of a average, you know, it's kind of a moving average of that. And here's a Hanning filter that not only goes down to 0, but also its derivative goes down to 0 as we're, you know, going to the high frequencies, and you get a very smooth looking kernel to filter the pictures. So here's an example of two activation maps. If I had some radionuclide in a container and it was a rectangular container, right? This is what it would look like with the Romlock filter, right? And this is what it would look like with the high frequencies taken off, right? And so these edges get smoother, right? As opposed to be just a straight edge here, they get smoother. And here's an actual example from, actually this is CT data where you apply the Romlock filter or something very close to the Romlock filter on the scanner. They usually never put a pure rectangle because the stuff just looks ridiculous. So but it still has those high frequencies there, and you can see a lot of this edge ringing off of here. And then this is with something that's close to a Hanning filter, right? So it smooths out a lot of the noise and it smooths off a lot of these artifacts off sharp edges. The convolution kernels can be approximated by discrete points that you convolve your projections with those discrete points. And in the early days, it was important to be able to do this accurately as accurately as you could quickly, right? In order to make a picture in a reasonable amount of time. When people were first doing this, you have to remember, like, array processors, as they were called back then, graphics cards used to be called array processors. To do a 512 Fourier transform, would take tens of seconds, right? So you really needed to make things efficient. And actually, convolution, you could hardwire it. You could make chips that just did convolution, and then they built chips that actually did back projection, just directly, right? And so those went into the scanners. And nowadays, it doesn't matter. You can do whatever the heck you want, right? Because you got infinite speed compared to those old days. When you look at these filter kernels and what they do to just a clean, brightness signal. So we have a lot of activation here, 0 in the background. The convolution kernel turns it into this function, right? Before you do your back projection, you get these bat ears on it. And this actually makes you susceptible to ringing artifacts at sharp edges. And then as the filters soften down, we get the peak of these bat ears goes down. Oh, yeah.
Well, what is exactly the point of doing the cleaning right here?
Doing the
cleaning using the discrete convolution kernels by technically convolving the signal with the kernel.
Yeah.
What's the real point of it?
Here, the point of it is, if you don't do this convolution and you just do back projection before, as we saw, you get a blurry picture. You get an incorrect estimate of the object. When you looked at the analytical function of doing this back projection, this convolution is absolutely required to get the function right, so that the right numbers are inverted. Right? So it's basically here is the accuracy of the data is required to do this convolution first. Okay, so that's I think what we're going to talk about today. And I think, I would read in Prince and Links, I would read about the basically projection slice theorem. They go into more detail in there. It's a little cumbersome in terms of the algebra, but it's probably worth getting that algebra in, so that you can work it through, and so that you just carry it around as something about the world. It's good to have that, right? And it actually was only proven mathematically or whatever, I think around the turn of the century, not this century, the one before. But and it was used in image reconstruction. Probably it wasn't used until the 70s, right? That theorem. And so it's fairly recent. that it was used in this way, but it is the most fundamental thing to know about CT, SPECT, and PET. Because all of those imaging techniques, what you do in the end is you reorganize your data such that it is in parallel bins, right? You take that data and you perform this, right? And so even if your data is being shot out in all weird directions, you collect all that data on your computer and then you reorganize it into parallel bins. And then you do the reconstruction, right? So, okay, great. Any questions? All right. So on Tuesday, we're going to do some nuclear medicine applications. And if you have any specific applications you want to talk about, shoot me an email. I can look them up. We can work it out. I will try and get the homework out this evening. Okay, so I'll put an announcement up when it's available to download. Okay, and you guys worked out a office hours, right, with the TA? Yeah. Okay. Yeah. Okay. Great. Okay. See you Tuesday. Oh, it'll be due. It's going out today, right? So it'll be due in a week. Okay.